In this example, we've got cerium 3D data that has intentionally been reduced. Each spectrum has been measured sufficiently long that we have good signal to noise, and we've got enough of these spectra that we can perform various operations to improve the quality of the spectral forms that we'll calculate. And the first step we'll do is perform a minor shift to each one of these data based on this isolated peak that we're going to place a background on, put a component and fit in order to try and identify the peak position. And we've propagated these peaks and these backgrounds to the set of spectra, and then what we will do is calibrate based on this component. So we're going to assign here, actually we'll assign an arbitrary shift based on an assignment for this peak position, which is not physically meaningful. It's just mathematically what we need to do to progress this calculation. So each one of these spectra have now been shifted based on the component peak. And then we've copied the shifted data. So we've now got another file that contains calibrated data, but each data bin is slightly offset by virtue of that calibration. So the next thing we'll do is we will perform an interpolation of the data so that we have data bins that all align with the intensities. And we'll use the spectrum calculator and we'll specify a range, so we need to know the VB indices involved. So if you look at the view menu, there's a way of displaying these VB indices, and that shows us that if we need to interpolate between VB0 and VB30. So having interpolated, you can see this is again created a new file. When we overlay these spectra, they are now in a form that we can do some linear analysis type calculations, such as principal component analysis. And the first step is we will use principal component analysis to eliminate some of the noise in these data. So the PCA calculation here is indicating we've got noise in the fourth abstract factor. So we'll reconstruct the set of spectra using 3 abstract factors, and you can see that we get a fairly nice sequence of noise reduced spectra from which we can do further calculations. And in this case, the calculation is going to be a series of different spectra. And the idea of the different spectra is that we should be able to eliminate perhaps some of the reduced form of this cerium and enhance the original state of this cerium before any reduction. And it helps if we know what these ought to look like. And we have 2 examples here of a cerium 3+ and a cerium 4+ spectrum. These were measured from standard samples, not this sample. These are other samples that give us an idea of what the spectra ought to look like. So when we search through this list of different spectra, we can see what the data set itself is telling us is within these data. So I've just identified something that looks like the 4+, and now what we need to do is look for the reduced state, and we're using the model of the 3+ as the form for the reduced state spectrum. So as we step through, we seem to identify something that looks about the same binding energy separation for the 2 peak structures, and there's certain evidence of a background shape that seems to be consistent here. So we'll choose one of these and then take a copy, and having identified 2 of these, we can then perform a least squares calculation to make sure that we've reproduced the original data set with these 2 spectra. So I'm going back now to before there was any PCA enhancement, and I'm going to copy these component spectra over and then perform a linear least squares calculation. For each one of these spectra in this sequence, we end up with 2 spectral forms that are reproducing each and every one of these spectra as they evolve throughout this measurement.